everybody. We are headed into the last lap of the conference, and to sort of start things off, we have got David Hoyle from the University of Manchester, who is going to be speaking upon a physicist approach to high-dimensional inference. Thank you, David.
Okay, can I just check microphone first? You can hear me at the back, yeah? Okay, great. Okay, so obviously I'd like to thank the organisers for inviting me to speak. I'm going to speak about a physicist approach to high-dimensional inference, which is a very sort of vague title, mainly because I didn't actually quite know what I was going to speak about until I'd seen sort of what other people at the conference or workshop were speaking about. You may wonder what a physicist, or particularly a theoretical physicist, is doing speaking to you on a statistics sort of workshop. You may also wonder more why a physicist is actually in a medical department. I often wonder that sometimes as well. So what I'll show you is obviously some of the problems that appeal to a physicist are actually being sort of motivated by problems in medicine and biology. And the work I'm going to be talking about is stuff which has been done with jointly with Magnus Rattray, who's also in at Manchester in the Department of Computer Science. Okay, so the motivation for this sort of the talk, if you like, is this sort of thing, a PCA plot. We've seen lots of people mention during the course of the week that various bits of biological and medical data are providing motivation. Examples where we have small sample size, high dimensionality. So, for example, gene expression data, proteomics data, metabolomics data. This is actually a PCA plot of some proteomics data. And often we might use PCA just to get a handle on this sort of experimental success. How is the experiment or set of experiments performing as we expect? So, do we sort of see some sort of clustering of points along the lines we might expect from our biological intuition? Does the data fall along the factors that we've been able to control for? So often we might just use PCA for a sort of sanity check, a visualization, quality control. Might also use it for sort of feature extraction, trying to construct some new representation of the data. There are obviously other situations where we might want to use PCA and sort of other sort of similar covariance-based dimensionality reduction methods on other types of data. For example, SNP data, single nucleotide polymorphism data. So we might want to use something like PCA to sort of correct for some of the factors that we haven't been able to control for. So remove some sort of the stratification in the data which would otherwise hinder our ability to detect differences between two classes. So, for example, this reference from Nature Genetics recently gives an illustration of essentially PCA being used on genome-wide association studies to improve detection. Okay. Well, I'm actually a physicist, so why am I talking to you today? Well, essentially, it's to highlight that some of the problems people have illustrated this week have actually been tackled in other branches of science already. Physicists have looked at some of these problems in a slightly different context. And the methods we use, because we're physicists, are approximate. They're non-rigorous. So if you like, we're doing high-dimensional inference, but often we don't quite know when we're correct, whether it's always going to work. We have to take a very sort of heuristic approach often. We try, confirm things by simulation. So it's not so much high-dimensional inference as maybe high-dimensional stumbling around. Okay. But what I actually want to point out is some of the results which are appearing recently in the high-dimensional sort of inference literature and the random matrix literature. Actually, you can obtain using theoretical physics approaches, statistical physics approaches. I think Peter Bickle mentioned on Tuesday, or used the word pathologies of large covariance matrices. So I'm going to talk about how you can evaluate some of those pathologies, obtain those pathologies using statistical physics. So my talk's actually going to start off with a little sort of brief introduction to statistical physics for those of you not familiar with it. Then I'm going to talk about these pathologies and how we derive them, and particularly the approaches that we use in physics to derive them. If I get time, I'm going to talk maybe a bit about the effects of finite NMP. And then actually to try and make contact with some of the topics which have been raised earlier in the week I think Michael Jordan mentioned about, was also speaking about reproducing kernel Hilbert spaces and the central role played by a Gram matrix. So I'll be talking about how Gram matrices, again, sort of naturally pop up in the physics literature where they're called Euclidean random matrices. So the overall aim of the talk is to sort of show where the sort of two branches of both statistical physics and the statistics literature are sort of coinciding, where they're coming together occasionally. Show you some of the techniques we use and give you a sort of guide to the sort of literature, what physicists have done on the same sorts of problems. We didn't always necessarily realise it was high-dimensional inference where we're looking at it from a slightly different angle, but you can see the similarities. Okay. I'm not going to try and defend the methods that we use from the point of rigour. They're not. What I'm going to try and do is try and get convince you of their utility of the methods that we use. So there's much more rigorous approaches you can use in some of these instances, but some of the techniques that physicists use are very adaptable. It's really a question of what's your sort of goal. I mean if you're very conversant with techniques of studying L1 regularization, then yes, go for rigor. If you're not, if you're interested in studying increasing levels of complexity of models, maybe you want to use more general sort of approximate techniques suggested by physics. As someone said yesterday, choose your religion. My religion is one of theoretical physics. Okay, so let's start off with statistical mechanics. Essentially, it's the study of large numbers of coupled objects, and I've been deliberately sort of vague in my use of the word objects there. Initially, essentially, it was started as the study of interacting particles. So it was originally used to study properties of fluids. So the interaction here is the sort of forces that you get between fluid particles, Leonard-Jones potentials. And obviously it has its basis in statistics. So for example, here the central sort of quantity in statistical physics is what's called the partition function, which is just a sum over various configurations. And typically we have an energy function. So here the partition function is a sum over configurations I, and there's an exponential weight here, and EI is the energy of the that particular configuration I. And if I can calculate this quantity, I can get to understand a great deal about the system, particularly when I've got large numbers of particles. So often we'll go to the limit where the number of particles is becoming infinite. So physicists always sort of prefer to evaluate partition functions. Here I've written it as a sum, but often you might write the problem down as an integral. So there's sort of all the techniques that physicists have developed are for essentially evaluating integrals over high-dimensional spaces. As I say, it's obviously originally developed to study properties of fluids, things like liquids and gases. But essentially, the techniques you've developed here can be applied to any system of interacting objects. Okay, so what could an object be? Okay, think of an example. I mean, some of you may be familiar with this one. You're driving down the road, a highway. The car in front of you brakes suddenly. The brake lights come on, and you suddenly have to slow down. Okay, so you're adjusting your speed according to the car in front. So that's a coupling between two cars, two drivers. So there's an interaction there. When you've got a high density of cars, certain behaviour happens. So when I drive home tonight, I'll get to about Birmingham on the M6, and suddenly it'll be gridlock because someone's hit their brake very hard. Okay, so that seems sort of interacting particles. Fairly obviously, we can consider data points as being interacting in some way, particularly if they're drawn from if they're correlated in any way. And it wasn't long before physicists were applying statistical mechanics techniques to other situations. And one area to point out is work by Sam Edwards on the eigenvalue spectra of large random matrices. So this is essentially a derivation using statistical physics to look at the Wigner semicircle law. Okay, physicists have had a long interest in random matrices. So the field of random matrices, obviously, sort of, if you like, well, started in physics as a way of trying to get to understand the properties of heavy nuclei. particularly their energy levels. And if you speak to any physicist, experimental, most people are familiar with the Wigner semicircle law. However, most physicists are probably ignorant of the sort of new work that's being done in the statistics community on limiting eigenvalue spectroforms for covariance matrices, things like the Tracy-Widom distribution as well. And I actually think it's a great shame that you've got these two communities that at one point have been together, had a sort of common motivation, diverged, and now sort of becomes in some ways ignorant of each other's works. Obviously there's some areas where the physicists and mathematicians and statisticians overlap, for example looking at random matrices and zeros of the Riemann zeta function. But the sort of physicists are largely ignorant of the more recent work on high dimensional inference, which I actually think is a great shame. Okay, so that's statistical mechanics. It wasn't long before physicists moved on to looking at problems of, say, learning. Okay, what do I mean by learning? I don't mean learning in the sense of, sitting down with a textbook. I don't mean education. I mean learning in the sense of machine learning, trying to sort of get one mathematical structure to mimic or pick out another mathematical structure. So I might have some data which is governed by a rule, a very simple one. It could be that the data is essentially lies along a direction B, and I've got another mathematical object, another vector, and somehow I want to get this vector here to learn what this vector here is from the data which has been generated from B. I mean, to this audience, I don't need to explain that this is essentially I'm trying to get J here to sort of mimic the sort of population, the leading eigenvector of the population covariance here, and we all know that given enough data, hopefully that J will essentially converge to B, using something like PCA. So J will be a good estimator of B. But as the talks throughout the week have illustrated, when you've got small sample size and high dimension, then PCA is not really consistent, and you've got a discrepancy between J and B. When physicists started looking at these sorts of problems, they weren't so much interested in, say, accurate prediction necessarily. You might be more interested in, say, what are the universal properties of learning. So that's why I've put up here statistical physics of learning as opposed to high dimensional inference. A physicist would be more interested in how does J sort of mimic B? How much data do you need? How do the different learning rules behave, particularly in asymptotic limits? So we always tend to be interested in universality. Obviously those things are of interest to statisticians as well, but physicists tend to sort of often would stop short of maybe producing anything useful. More interested in actually studying the theoretical properties, particularly for large systems. And a lot of this work was done sort of in the mid 80s, early 90s, and by now there's a sort of a mature literature out there, and so I've illustrated some sort of key texts. My favourite is this one by Engel and van den Broek, Statistical Mechanics of Learning, came out in 2001. Other books, for example, Advanced Mean Field Methods, which goes on about mainly variational methods. Some of you may also be familiar with the book by Hertz, Palmer and Crow, which isn't so much a book on statistical physics of learning, but it does actually sort of introduce some of the techniques from physics within it. And David Donahoe's already mentioned the book by Nishimori. So if you do actually want to learn more, I'm going to be able to give a very brief taster to sort of what physicists do. Then if you want to know more details, then that's a very good book to start off with. Okay, so here's our sort of the systems we're working on. And to be really unhelpful, virtually every symbol that a physicist uses is different from a statistician's. So N and P are the wrong way around for a start. My data points, xi, okay, live in R to the N, okay, and my sample size is P. And often in real examples, P is very much less than N, but in the analysis we don't have to necessarily restrict ourselves to that. Okay. I used to give talks sometimes to the statistics audience, sometimes to computer science audience. Computer scientists tend to use D for dimension as well. So some of my slides I try and change around. So some of my slides I used to have P and N, then N and P, and then P and D. And by the time I've gone through about a year and a half of different talks, I've got so many slides mixed up, I don't know what I'm talking about. So I've reverted all the way back to physics notation, I'm afraid, all the way throughout, including what expectation operators. C's my population covariance, okay? I'm not going to make, all I'm going to do is I'm going to apologise for not being more apologetic, okay? Tough, you're going to have to get used to the notation. Okay, so here are my data vectors, drawn, live in R to the n. Okay, they're drawn from IID from a multivariate Gaussian, zero mean, population covariance C. My population covariance, sort of thing I might want to be studying, particularly motivated by that figure on the last slide, okay, has this form. Essentially, it's dominated by identity matrix. So essentially, it's a Gaussian ball, Gaussian cloud, if you like, except for this term here. So B is a unit vector. So I've got some distortion of that Gaussian cloud, that spherical cloud. A is a positive number, so along some direction I've got a slight stretching of the cloud. Depending upon the size of A, the bigger A, the more stretched it is. And obviously this introduces the notation, the notion of sparsity again. If I knew what B was, I'd be able to pick a suitable coordinate system, and I'd have a very sparse sort of reasonable representation of the data along that axis. If A is very large, I've got a very elongated data distribution, and I'd hope that my algorithm should be able to pick out that direction very easily. Okay. Yeah, so that's my population covariance, and I'm going to draw data from it. Okay. Now I'm going to use essentially what is PCA to try and see if I can learn that direction B. That's what I'm interested in. So the way we might do it is say, okay, well if my vector J is trying to mimic B, and essentially B is used to generate the data, then essentially what I want to do is get J to recover as much of the data as possible. This is just maximal variance learning. So I'm projecting my data points psi mu onto J. So each one of these is a projection of xi onto J, or the other way around, whichever way you want to look at it, essentially squared, and I'm summing up over all the data points. And I want to adjust J so that this quantity is maximized. Okay. So J will actually obviously come out to be the leading principal component of the matrix formed by these vectors. So essentially it's the leading principal component of the sample covariance matrix. Now you may say, well, this isn't actually the sample, this little bit in here when summed over the data points is not actually a sample covariance matrix because I haven't subtracted off the sample mean. But my data is actually drawn from Gaussian with zero mean, and ultimately I'm going to go to the asymptotic limit, so that sample mean will also vanish. So all that's going to lead to is order n to the -1 corrections, and I'm going to be lazy because I'm a physicist. I'm not going to, I'm going to analyze this quantity. You can actually put the sample mean back in there and it all goes through correctly, and you draw exactly the same conclusions. Okay, so J is going to try and learn the direction B by maximizing this quantity. I can measure how successful that learning process is by just looking at the scalar product between B and J, and I'm actually looking at the square of it because what I'm going to do is average over lots of data sets. And since J and minus J are equal solutions to that optimization problem, when I average over data sets, I don't want them to cancel it out, so I want to obviously average a positive quantity. Okay, so here comes the physics bit. What do? Well, we look at the asymptotic limit. We've all heard about this during this week. N and P going to infinity. Remember, N is my data dimension, P is my sample size, so I'm looking at P over N being some stable fraction, alpha typically less than 1. Okay. Why do we do that? Well, physicists do that not because they were motivated by high dimensional inference, okay? It's because it's easy. That's what we do. It's the thermodynamic limit. That's what we're used to studying. You're used to studying lots of objects, okay? So essentially, we've always been doing high dimensional inference, okay? But we weren't necessarily trying to be helpful to high dimensional, people, statisticians. It's just what we do, okay? And often in this limit, the systems that we look at are characterized by a smaller number of variables, order parameters. And for each data set, I can look at this quantity R squared, which tells me how accurate the learning is, and I can average over data sets to get expected results. And how do we do that averaging? Well, we're going to use various approximate techniques. Physicists' favorite one is mean field theory. And a sort of variation on that is, well, part of that machinery is a thing called the replica trick, which David Donahoe mentioned in his introductory talk. on Monday. Okay. Some of you may have heard of the replica trick, some of you may not have done. It draws a great deal of sort of derision from the statistics and mathematical community. Okay. It's not rigorous. Tell me something I don't know. Okay. Yeah, we can't defend it. Okay. It's just it's useful. It's nothing. There's no sort of real magic behind it. It's actually quite a simple idea. And so I'm actually going to talk through an example of how you actually use it on one particular calculation. Just to expose you to it. You may want to use it, you may not. Other techniques that physicists use is a thing called a cavity method, which is less used, and I won't talk about that today. Okay, so if I do that sort of learning process, looking at data sets, extracting the first principal component and seeing how well the principal component compares to the actual leading eigenvector of the population covariance, then this is the sort of results I get. Okay, so what I've got plotted here is R squared, and this is actually averages over lots of data sets. So each point is a simulation, an average of simulations. So I've taken a particular value of alpha. That tells me how many sample data points I've got in my data set. I've taken dimensionality n equal to 1,000 in this case. I've generated a data set, done a PCA, compared the leading principal component to that vector b, calculated R squared and averaged it again over 1,000 data sets. And what you get is this curve here. The physics theory gives you this solid line here. It's actually 0 along here. So the first thing that you should interesting thing that pops out of this is this phase transition. Okay, for small sample size, i.e. small alpha down here, the expectation of R squared is 0. So here's my population covariance, and the PCA gives me something like that, completely orthogonal. Okay, which is what I think Peter Bickle was saying on Tuesday, which is rather worrying. You know, you learn nothing about the underlying data, even though you've got some sample data. So you would, naively, not being a statistician, yes, I wouldn't expect to learn B perfectly, but I might expect to have got somewhere close to it. You know, I wouldn't have expected it to be 0. Okay, but once we get to a certain critical value of alpha, critical sample size, we begin to learn the actual direction B. So this is actually recorded in the statistical physics literature as a retarded learning phase transition, because learning of the direction is delayed. Okay. Okay. You'll notice the discrepancy between theory and simulation. Up here it's not too bad. I think the sort of size of the fluctuations is of order of the size of the symbol I've plotted. So there is a small bias here. It's going to be of order n to the -1 because this is actually simulations on a finite sized, finite dimensional data sets. The discrepancy here is more interesting actually, and I'll try and get to talk a bit about that later on. So some of the stuff that Boaz Nadler talked about on Wednesday will give you some of these deviations, and in some cases what the machinery that Boaz has got is more powerful than the way a physicist would tackle it. But I'll show you the physics approach to how you would evaluate this discrepancy here. Okay, so all this work, this sort of theoretical line here, was actually derived in the physics literature in the sort of mid-90s. I've done some work of it on it more recently. Again, using replicas, so non-rigorous approaches. But even within the physics literature, there is actually a rigorous derivation of the existence of the phase transition. So Manfred Oper and Didier Hershkovitz have actually derived rigorous existence of the fact that you have a retarded learning phase. You don't necessarily get the shape of the curve, but you work out that the fact that there is this phase transition occurs. Okay. One thing to realize from that immediately is, well, that phase transition is telling me that J, my vector, my principal component, which is trying to mimic the population covariance, is changing somehow at that transition point. Well, the quantity I've maximized is this thing here. Okay. Well, essentially that's just the Rayleigh quotient of this matrix here. Because remember, J, I'm going to restrict to unit length. Okay. This quantity here is my sample covariance matrix. So if the Rayleigh quotient, the maximum value this attains, once I've done that maximization, gives me this thing here, gives me an estimate of the top eigenvalue of the matrix here. So once I've done that estimation process, once I've done that maximization, I've got an estimate of the top eigenvalue. And because J is changing in behavior at that transition point, that immediately tells me that the phase transition in sort of R squared implies a phase transition in the top eigenvalue. Okay, and again, if we look at the actual eigenvalue structure, we did see a phase transition structure in the eigenvalues. So here's a set of eigenvalues from a sample covariance matrix. I've got a reasonable sample size here. My alpha is reasonably large. I think it's about 0.5 here. And I've just plotted the top eigenvalues against essentially rank. Okay, so the first eigenvalue is having a very different trend to the remaining eigenvalues. So this is high alpha, high sample size. I'm above that transition point. At smaller sample size, lower alpha, the top eigenvalue doesn't appear to be any different from the other remaining eigenvalues. And if I plot all the remaining eigenvalues of distribution here, what I get for the bulk of them is this distribution here. So this is actually from a single data matrix. So I've got a single data set, calculated the sample covariance matrix, and then just obviously done the eigenvalue decomposition. The distribution here, the solid line, which the data actually follow, the simulation follows very well, is the Marchenko-Pasteur law for that value of alpha. So those of you familiar with Marchenko-Pasteur and random matrix theory will recognize that shape. I'm going to talk about it a bit more. Peter again spoke about it on Tuesday, wasn't it? Tuesday, I think. And essentially what's happening is in this situation where I've got limited data size, okay, my top eigenvalue is somehow sitting at the edge of the spectrum. For larger sample sizes, my top eigenvalue has popped out and is somewhere beyond this edge up here. So in other words, if I know where this point here is, this edge of the bulk of the bulk spectrum, I can use that as a way of determining how much signal I've got in my data set. If I see any sample eigenvalues which are beyond this edge, then to me that represents signal in a very crude way. And that was suggested a long time ago by Kenneth Factor in the statistics literature in the mid-70s. Okay. So this existence of a phase transition structure in the top eigenvalue appears in the physics literature in 2003 and a bit more in 2004. As far as I'm aware, that's the first example in the physics literature. Okay. So that's the phenomenology. Where's the connection to statistics? Well, the sample covariance matrix I've looked at is what's called essentially an example of a spiked covariance matrix. It's a term coined by Ian Johnston in an Annals of Statistics paper in 2001. Why spiked covariance? Well, I'm assuming essentially it's because if you look at the distribution of your population covariance eigenvalues, you've got two Dirac delta function spikes, one at sigma squared and one at sigma squared 1 plus a. Okay, so you've got your distribution in the population is spikes. Obviously, the sigma squared corresponding to the isotropic part is very much larger than the signal part, and will obviously depend upon the data dimension. Okay, all the stuff that I've shown you in the past couple of slides, which was obtained in the physics literature, maybe from the mid-90s onwards, has actually also been obtained in the statistics literature. So probably the first sort of rigorous proof of the results I've shown you was obtained by Debashish Paul, just recently come out in Statistica Sinica 2007, but the technical report was on his website about 3 or 4 years ago actually. And obviously that work has been carried on in the statistics community by a number of researchers, Johnston, Baik, El-Khoury, Bai, Silstein, Sondri and Pesce, and so on. Unfortunately within the physics community I think I'm a lone voice. And as I say, it's one of these unfortunate situations where a lot of physicists are unaware of this emerging literature. Okay. In general, we can go from just having a single direction in which we've elongated the Gaussian sort of sphere to where we elongated along many directions. So in general, our spiked covariance matrices might have many orthogonal sort of signal directions. So what I'm imagining is that I've got a sort of isotropic covariance matrix, and to that I'm adding a small perturbation. S may be a small number, low rank essentially. S might be 2, 3, 4, and I'm adding a small low-dimensional subspace to my isotropic covariance. So I'm elongating that Gaussian cloud in many directions. But as I go to the asymptotic limit, I'll always keep S fixed at some small number. Okay. So here's the thing about the Marchenko-Pasteur law. I said it was if you knew the edge of the bulk spectrum, you've got a means of estimating what's the dimensionality of your signal in your data. The bulk spectrum only depends upon the value of alpha, and here I've got some plots for different values of alpha. When alpha is very small, we've got a very elongated spectrum. So this is essentially taking data from an isotropic population covariance. So all my population eigenvalues are essentially 1. But even my sample covariance eigenvalues can be as way up here. There's a huge bias. Okay, this is known as the Marchenko-Pasteur law, and one way of calculating it is through the Stieltjes transform of the eigenvalue density. So rho is the quantity we're interested in. M is its Stieltjes transform. If I know M, I can essentially invert the transform and get rho. But it turns out there's a very nice simple relationship which connects M to the eigenvalues of the population covariance. It's this law obtained by Marchenko and Pasteur. Also again obtained by Genefactor in 1978 in an Annals of Probability paper. Actually, if you read this paper, it actually gives a lot of nice little insights that don't appear in the Marchenko and Pasteur paper. I've got to admit, I struggled to follow the Marchenko and Pasteur paper. And in fact, it's actually been derived also in the physics literature, probably from about 1978 onwards, several times. There's at least 3 different branches of physics which have discovered this law and haven't told each other. And I've actually lost track of some of them myself. Okay. If we're looking at the sample, if we're looking at these spiked covariance matrices, then this relationship is very useful, because if I've got a spiked covariance matrix, and let's go to the simplest case where I've just got isotropic covariance matrix, then my population covariance is just a delta function. Plug that direct delta function into that integral, extremely easy to evaluate, even a physicist can do it. You get a quadratic equation relating m to z, and I can solve it. Once I've got m of z, I can use it to invert to get rho, and then it gives me this form here. So it's a very powerful, very powerful relationship. Okay, so that's the sort of phenomenology. That's the sort of connections to the statistics literature. As I say, I'm going to show you actually how physicists calculate those quantities, how we calculated that phase transition learning curve, how we calculated that retarded learning phase transition, and how we calculate the Marchenko-Pasteur law. Okay, it's probably easiest to do it on an eigenvector calculation. So as we said, this is the quantity I maximize when I'm trying to work out the properties of the first principal component. So xi are my data points, j's a vector which when it maximizes this quantity was equivalent to the first principal component. Okay. As a physicist, I don't tend to like optimization. All my techniques I've developed I'm familiar with are used to evaluating integrals because I like partition functions. Sums or integrals I can handle, optimization a bit harder. So I'm going to convert this optimization into an integration problem. So first of all, I introduce a distribution of vectors j. What I'm doing is got a term out here which is essentially just restricting the length of j to be 1. I'm only interested in unit vectors. Then I've got this exponential quantity here. Beta is a positive number. So the most likely value of j within this distribution is the value of j which maximizes this quantity, which is exactly the thing I'm interested in. Okay. So when beta is very large, this distribution is going to be very highly peaked around the value of j which maximizes this bit of the sum. Okay. Yeah. Okay. What I'm ultimately going to do is take beta going to infinity. Okay. And I'm hopefully going to pull the wool over your eyes. I do all the calculations, assuming essentially beta is small, so some of my integrals converge, and then I'm going to analytically continue. Within physics, there's a lot of what I call analytic continuation, and when a physicist speaks about analytic continuation, we mean we just suck it and see. Does it work? Great. If it doesn't, okay. We don't look at necessarily proving analyticity. We just try it. Okay. The quantity z is just the normalization factor for this distribution, what physicists calls the partition function, so here it is. Okay. The term here, h, is what the physicist calls a source term. By taking derivatives of the log of z, I can use that to give me work out expectations of various powers of R, of this B, the scalar product between B and J. Okay, so ultimately I'm going to take H to 0, but probably from above. Okay, so if I actually want to work out how J behaves, all I have to do is work out log Z. And if I want to work out how J behaves when averaged over lots of data sets, all I have to do is average log of Z over data sets. This is a physicist notation for average, for expectation. These angle brackets means expectation over data xi. Okay. Trouble is, this is a nasty quantity. Trying to take the average of a log is a very difficult thing, often. I mean, you could sort of invoke maybe some sort of inequalities if you want to. Okay, but I try and prefer to get some more accurate handle on it. Okay, so this is where the replica trick comes in. Again, if you're looking for rigor, close your eyes. Okay. The replica trick just involves a representation of log of x. So log of x, we can write there's a limit of x to the n minus 1 over n in the limit of n going to 0. So there's sort of implicit in that is that n is continuous, n is real. Okay. There's another way I can interpret that is to say, well, x to the n is just x times x times x times x. Okay. So it's n products of x, it's n copies of x. Okay, but here I've made the assumption that n is integer now. Okay, but the idea is that x to the n is n copies, n replicas of x. So what we do is we try and evaluate things with integer numbers of x, and if we can work out what the dependence on integer numbers of x as a general sort of function of n is, we then sort of continue from integer values of n to non-integer values, and we continue all the way down to 0. Okay. Again, extremely non-rigorous. Sometimes it works, sometimes it doesn't. Okay. So the things I had before, my integration was over that I was interested in was an integration over a vector j. Now I'm going to introduce replica copies of it. So I'm going to denote them by a subscript nu. Okay. So essentially what I've got is this quantity here. This is my integral I had before, except now I've got little n copies of the integrand, all indexed essentially by this subscript nu. Okay, the term here is just the sort of averaging over the data, over my Gaussian distribution of data. Why do I like this approach? Well, now this integral is tractable. It's Gaussian all the way through. Okay, so I can actually do that integral. And what I get is this form. The matrix M is very easy to evaluate. For the sort of simple spiked covariance matrices we were studying, I can evaluate the matrix elements directly, very easily. You'll notice that it depends upon quantities such as the overlap between the vector I'm trying to learn and the various copies of my sort of vectors which are learning. Okay. The original integration is over J. The integrand depends upon R and these Q's. Okay, so I'm just going to do a change of integration variables. And what I now get is my original integrand, a Jacobian factor. Okay. Integrating over the R's and the Q's. Okay, but the key point to realise is that when I go to the high dimensional limit, i.e. n becoming very large, I've got this n outside, a large positive quantity outside the sort of the exponent, okay, or as part of the exponent. Okay. To any physicist, or that's crying. That integral is now crying out to be evaluated by some sort of saddle point expansion, because we're assuming n is large, and therefore, as n becomes very large, the saddle point expansion should converge very rapidly, or could converge, and we can get the leading order term, the asymptotic limit, just by looking at the saddle points of this quantity here. So the next assumption we make. Is to say, well, can we assume something about the saddle points of this exponent? And we assume what's called replica symmetry, namely the saddle points, the relevant dominant saddle points, all have the same value R nu. It's just given by R, and likewise for the Q variables, that the saddle point, the relevant saddle points, have the same value given by Q. So I've changed it from an integration over many quantities into essentially, by plugging in this ansatz, to a problem in just to sort of working out stationary points in two variables, R and Q. And again, that's the sort of thing I can handle very simply. If I can locate the stationary points with respect to R and Q, it gives me an approximation, a saddle point approximation to this integral, and as I said, that integral then allows me to sort of estimate the behaviour of R by taking essentially looking at essentially looking at log z and in particular taking the number of replicas n going to 0. Okay. Okay. I won't dwell any further on it, as into how complicated it is to solve this, find stationary points of this exponent. So it is usually relatively simple. The key point I want to get across is the use of the replica trick for evaluating averages of logs, and also the assumption of replica symmetry, because they're the two ingredients that we often, put into a physics calculation. And it's exactly that approach which we used to derive that learning curve. And in fact, that was precisely the calculation which was done in the Riemann paper in the mid-90s. Okay, I'm going to have to watch my time. Okay, how can we evaluate eigenspectra? So I've spoken about how we might use the replica trick to evaluate the properties of the first principal component, but how do we actually in general evaluate the properties of the eigenvalues? I used that argument with the Rayleigh quotient before, but I want a more general technology to come into play. So imagine my sample eigenvalues, my sample covariance eigenvalues are lambda I. The empirical density is just a set of delta functions based around those values. I'm actually interested in the average sample eigenvalue density. So I'm going to take an average over data sets. And the way I do that is by introducing this thing called here the resolvent. So essentially what I'm interested in is essentially looking at 1 over lambda minus the sample covariance eigenvalue lambda I. And this looks very similar to the Stieltjes transform that we had a few slides ago. And in fact, essentially it's a very similar approach. I can actually write this quantity as the log of the determinant of lambda times the identity matrix minus c hat. C hat's my notation for the sample covariance. So the eigenvalues here are just the eigenvalues of this matrix here. Okay. If I perturb lambda slightly off the real axis and then look at the imaginary part and take the perturbation going to 0, then essentially that will give me my set of delta functions that I'm interested in based around the various sample covariance eigenvalues. So all I have to do is average this whole quantity over data sets. Okay, and I'm using this representation for trace of G in here. So ultimately it boils down to averaging over data sets log of a determinant of a matrix which involves the sample covariance matrix here. So it's getting close to the sort of things I'm used to as a physicist. It's an average of a log, but it's an average of a log of a determinant. Okay, how can I convert that into an average of a log of an integral, which is what I'm more used to evaluating? Well, I just use this little trick here that obviously the log of a determinant of m, introduce a -2 here, -1/2 here. They cancel out when I essentially bring that down with the log. Okay, and a determinant of this quantity here, I can just write essentially as an integral over a Gaussian integral over some vector. I've dropped factors of 2 pi obviously because I'm not interested in those. So by plugging this into here, I can actually get the whole expression down again to a single calculation where I have to evaluate the average over data sets of a log of a Gaussian integral. And again, I can just use then the replica trick to do that log part of it, averaging over logs. So there's a sort of technology here that we can use to evaluate eigenvalue spectra, sample eigenvalue spectra. And this is the approach we use in physics. We use it over and over again. Okay, I'm not going to show any more theoretical calculations. I'll just show you some sort of results that come out. So the retarded learning, yeah.
So when you do the calculations, right?
Yeah.
It's a formalism. You don't know that the answer has all these properties.
Yeah.
So somehow that makes people who have let's say, a math analysis background
Nervous.
But physicists don't seem to worry about it.
Well, I mean, there are some ways of checking for the validity of particularly the replica symmetric ansatz you plugged in. So you can check for instability to sort of replica symmetry breaking. The overall use of the replica trick itself is a bit more difficult, and I'm not familiar with of any sort of real good work which says when it isn't really applicable, when it isn't going to work. Often you're guided by your own intuition about the symmetry. So something like this, where I'm looking essentially at eigenvalues of PCA, which I think of as being maximal variance learning, where I've got a simple sort of if you like, objective function I'm trying to maximise, then in those cases my sort of intuition would be that yes, I expect it to work. In general, no. I mean, you just try it by comparing against simulation.
What other small I always thought my dad was they have some feeling about fields and forces and things like this. And to me, to see physicists doing formal calculations without having some physical meaning what all of these quantities are,
Yeah.
is a little strange. What are the replicas? What's the interpretation of the whole process?
Okay. I mean, in this case, I sort of think of replicas as being, if you like, precisely what it says, a replica. I think of it as being many sort of student vectors trying to copy the direction B that's been used to generate the data. And since sort of when you're doing PCA, there's essentially only one solution. I would expect in this case that the different student vectors, the different replica vectors, are not going to get confused. They're all going to fall to that one sort of global minimum. So in this case, this is one situation where sort of a bit of prior intuition does suggest that you expect it to work, but as to where the forces are, here it's not so much obvious. So obvious. It's a bit more. You have a bit more intuition about the free energy that comes out sometimes. I can't really sort of make general comments about in response to that. Yeah. Okay. Okay. So here's the. If we just look at a situation in the spiked covariance matrix where I've got two directions in the population covariance. So I'm looking at the first two principal components, and this quantity here is the overlap between the first principal component and the first direction in the population covariance. This quantity here is the overlap between the second principal component and the second eigenvector in the population covariance. And again, each one has a retarded learning transition. The form of the retarded learning transition is essentially universal. In Martin Wainwright's language, I could get these to sort of stack on top of each other if I wanted. Essentially, the only thing that which controls them is the size of the signal strength A. So the degree of elongation. So this first direction here is more elongated, easier to pick up than the second direction given by this second curve here. And again, I think these results are also sort of been replicated in the statistics literature. And again, we have phase transition in the eigenvalue structure. So that was eigenvectors. Here are the eigenvalues. Here I've got a population covariance with 3 directions. So I've taken that Gaussian cloud and I've stretched it in 3 directions. And given enough sample data, I can pick out 3 sample eigenvalues which are very different from the rest. The remaining follow the Marchenko-Pasteur law again. Okay. I'm going to skip on the finite NMP just to catch up. Okay, so I want to move on to. Okay, so I'll mention this slide. So, what I've shown you is very much talking about, largely about PCA. Okay, but there's an awful lot of other work within the statistical physics of learning community on various other systems, many of which are relevant to some of the situations or problems that were mentioned during the week. So there's obviously the sort of seminal work by Gardner in the late 80s on the perceptron, and I've put various there because there's just too many references to list. If you want to go for a good sort of introduction, again, read the book by Engel and van den Broek. The SVM essentially studied, or the reference I know of, by Opper and Urbanzik, a NIPS paper. Someone mentioned earlier in the week about looking at ICA. You know, what scaling of data do you need to sort of get ICA to sort of, you know, learn the appropriate directions. Again, that problem's been studied by Urbanzik, fairly recent, 2003. The scaling's not linear, so you're not looking at NMP scaling, you know, a fixed ratio. And the analysis here is one which uses the cavity method, because the replica trick actually breaks down in for this calculation. So these are sort of, you know, sort of machine problems that are interesting to machine learning people, which is where you tend to get the majority of people in majority of physicists concentrating. But also some people have, you know, addressed, you know, things which might appear to be more standard statistics. For example, looking at accuracy of bootstrapping, etc. So there's a nice paper by Manfred Opper and JMLR from a few years ago. The last thing I want to touch on is what are called Euclidean random matrices in physics. Essentially, that's just a Gram matrix. But there was a nice paper from 1999 by Marc Mézard and Parisi in the physics literature, which essentially worked out the eigenvalue distribution and for a Gram matrix. And Magnus and I sort of adapted it to actually make it a bit more applicable to sort of machine learning scenarios. The original motivation for Mézard and Parisi was fluids, so essentially low-dimensional, uniform. Yeah.
I'm not sure. What's the difference between a Gram matrix and a covariance matrix?
Okay, so a Gram matrix, I'm just taking the matrix. The matrix elements are formed by the inner product between the different data points. So I'm looking at data points, not features. Yeah. Precisely. I mean, the way all those calculations I've done on the previous slides is actually to look at the Gram matrix. So essentially, I'm looking at it, you know, yeah. I mean, the non-zero eigenvalues of the covariance matrix will be the eigenvalues of the Gram matrix, and so it's easier to work with the Gram matrix. But in general, when we're looking at things like, you know, kernelized versions of learning algorithms, then you're dealing always with the Gram matrix, because you know some of the things we're interested in doing is mapping from our original feature space into some other higher dimensional feature space, and we can do that. We can work out inner products within that new feature space by specifying a kernel, a positive definite kernel. Okay, where Gram matrices occur in physics is these Euclidean random matrices. And a Euclidean random matrices is just where the matrix elements are formed by some function of the Euclidean distance between the positions, the data vectors x, x1 up to xp. The reason physicists are interested in that is that we can think of k being something like a interaction potential between fluid particles. So if you're familiar with fluid physics, k might be something like the potential of mean force, or a Mayer-F function. So essentially, the original analysis done by Mézard and Parisi was looking at low-dimensional systems, essentially R to the D, where D was, say, three-dimensional, and where the distribution of points was uniform. You're looking at a bulk fluid. Okay. Again, we can use the resolvent to calculate the eigenvalue spectra. So if I know the resolvent, I can get the eigenvalues from it, the eigenvalue density, in the way that I outlined a few slides ago. And the resolvent can be formulated in terms of a derivative of a log of a replica partition function. Here's the replica partition function. So again, I've done some few tricks to get it into this form. I'm not going to go through those tricks. Just want to point out again the use of replicas. So there's an index here, new, and my integrand is essentially identical, but I've got multiple copies which are only sort of differentiated by the value of new. Okay. So once I've got it in that form, I want to approximate that integral. I want to simplify it somehow, and I could do it by saddle point approximation. But the way in which Parisi and Mézard went about it was actually to do a variational mean field. They used to approximate it by some sort of Gaussian form and then adjust this quantity here so that you sort of get as tight a bound as possible. When you've got a quadratic approximation like this, in physics it's known as the RPA, the random phase approximation. There's also other ways of deriving it. So for example, I could actually expand in this quantity here, omega, which is effectively like the number of particles, the number of sample points, and then re-sum particular terms within that expansion. The reason why I do that is that physicists have known for a long time which diagrams to re-sum to actually get the RPA. So I knew two ways of how to do this approximation, and you know, I could show that they coincided. And what I get out is again essentially a relationship like the Marchenko-Pasteur law. So here's my resolvent, here's a quantity z, which is like the eigenvalue I'm interested in, slightly perturbed off the real axis. This quantity here, the lambda n, are the eigenvalues of the kernel. So if I know the kernel and I can evaluate its eigenvalues, I just plug them into this quantity here. D's the degeneracy of that particular eigenvalue, and then all I have to do is solve that equation. To show you some simulation results, here's data uniformly distributed on the sphere. I've got a Gaussian kernel, which essentially, because I'm talking about on the surface of the unit sphere, is just a dot product kernel. Two plots, one low amount of data, the other a high amount of data. So here I've got 10-dimensional data, here again 10-dimensional data, but here I've got 50 sample points, here I've got 100. So you can see as I get more sample points, I'm resolving more and more structure in the expected eigenvalue density. And again, I see these phase transitions. So as I add more data, I see separation of particular parts of the spectra away from the remaining part. So here, when I've got a low amount of data, I've got this bulk here, and I've got the beginnings of the emerging part here, but it's still joined. As I add more data, they separate out and they begin to converge to the actual population eigenvalues. So again, I could perhaps use this as a very crude way of saying, okay, how many data points do I need to actually sort of learn parts of the sort of underlying sort of kernel, if I'm interested in that. Okay. Again, here's another simulation. Again, this time I'm looking at very much lower dimensional data. I'm looking at essentially two-dimensional data. Again, here I've got a large sample size, here I've got a lower sample size. When I've got a higher sample size, I can resolve many more peaks, very many more sort of bits of the eigenvalue spectra. Okay, and I better finish quickly. Okay, so to summarise, as I said, there's a fair number of common areas between statistical physics and the inference of statistical inference when dealing with high-dimensional data. In some cases, statistical physics and statistics have diverged and not really come back together, which, as I say, is a bit, a bit of a sad situation. The high-dimensional limit sort of situation that has been spoken about during the course of the workshop, where we're looking at n and p going to infinity, is the natural one that physicists always study. And hence we've got a lot of tools already developed for sort of looking at these sort of situations. The techniques are useful for studying both the asymptotic limit and also the finite size effects, which I didn't really get a chance to cover. The methods aren't rigorous. There's no way, even a physicist could look at some of the approximations we, introduced here and the way we've interchanged averaging and differentiation and sort of done the various analytic continuations. And there's no way a physicist could defend them as rigorous. And often they do require some physical intuition, particularly about the various sort of underlying symmetries within a system and how you expect the system to respond to those symmetries. However, I'm not going to try and defend the methods upon rigor because I can't. What I'm hoping I'm going to get across to you is A, the utility, show you how they're used, and also give you a guide a bit to the sort of where physicists have gone before and where they're going. And with that, thank you.
We do have a minute if there are any questions. Yes, Mike.
In the physics literature, there are things like the mean field approximation, and then you can go beyond that to Betti approximations.
Yeah. Yeah.
If if you regard the replica method as if you like, simple to use tool, the same way mean field is there a kind of a next order of approximation to go to from that?
It's still involving replicas, or
Well, still involving something you can actually calculate.
involving replicas, I'm not so sure. I mean, so typically, sort of, physicists would, if they were looking at higher order terms, might develop some variational approximation and then go to these sort of TAP equations, so higher order mean field equations. When using replicas, no, I wouldn't say there's a great deal out there, or not that I'm familiar with.
Conceivably, Mike means maybe replica symmetry breaking. The replica method is kind of the easiest under symmetry. Then you have to be significantly more invested in this way of life in order to go.
Yeah, okay. But
and that's more accurate.
yeah, but I would say, I mean, the replica, when you've got replica symmetry breaking, you're still doing a replica calculation. It's just an assumption about what the structure of the dominant saddle points are. You still use the replica trick to try and approximate the log of an average. Sorry, average of a log. It's just a question of whether you're happy making that assumption that the dominant saddle point is symmetric. If it's not, then yes, you're going to have to go to one-step replica symmetry breaking.
In the replica method, be justified under some circumstances, that would be continuation.
Well, there's work by Talleyrand that tries to justify the use of replicas. I mean, I don't try and usually invoke that work because I'm not sure how general it is to all the sort of systems that physicists apply the replica trick to. So again, I'm not familiar with sort of any general sort of work which gives some more broad justification to the use of replica trick. And physicists don't. We just again, it's very much a try it. So for every replica calculation, you've got to verify it by simulation at least. So in contrast to what David was saying about in the electrical engineering literature, where they take it as given that replica calculation is correct, physicists won't, or at least not any physicists that I know of. I mean, we're aware that it's flawed essentially in a lot of situations.
Well, I didn't say they take it as correct. I think it goes like this: you do the calculation, and it's a publishable thing to say, here's the result. Then they do some simulation, and they see something work in that. But they're allowed to publish it actually stated as a theorem that what the conclusion is. And then the proof has replica method in it.
Okay.
So that
I would never cite. I mean, all the stuff I've cited in my own work, none of that is theorems. It's derivation. So I'm quite happy to say that yes, I've obtained the result. I may have obtained it early, but the rigorous proof is Johnston, Devashish, Paul, etc. But I'm a physicist. I'm interested in sort of moving rapidly through a problem and sort of developing maybe more complicated complex models and adding some extra features to it where maybe it might be a bit more tricky to study using a rigorous approach. It's a trade-off. You've got utility against rigor. With utility, you can make rapid advances. But yeah, I mean, I agree. It's not theorems, but they're results.
Are there any other questions? If not, let's thank David again. Poster presenters